All right, welcome back. Class number four, February 12th. And again, winter seems to only happen for us on Wednesdays. So, Zoom class. Thanks again for your patience with moving to Zoom. It's been I know we're in Iowa and we should expect snow and stuff, but I still have this motivation to try to, if school buses aren't running, I feel like it's probably a good idea for you not to be out there if you can avoid it as well. So that's my motivation for it. I hope you're okay with that. Um, that being said, I just wanted to make a few notes. I mentioned this last time. February 26th, I'm going to have some type of video for you to watch, probably an introduction to JAGs. We're going to be getting into Bayesian at that point. I won't be, I'm scheduled to be in Germany at that point. So that's why that's happening. But I want to keep the class moving and not drop it, topics from the list as much as possible. As you're all aware, certainly at office hours, let me know that you're aware. We got a homework due on Friday. I will reiterate. I'm happy to answer questions for you over email. I'm happy to work with you. I may not have made that very clear prior to this, but let me just note that when I give you an assignment, I sort of look at that as a, if you don't know something, I welcome you to come talk to me about it. I want to be your teacher. In fact, teaching is one of the best things about this job, and working with each of you is a joy. And so, me being able to have an opportunity to do that is sort of how I see that. So, um, you see that coming up Friday, so hopefully that won't be too bad for to do. I've also sort of lengthened the homework schedule. So homework two is going to be coming out on Monday, but I'll talk about it in class next week. It should cover what we're talking about last week, and today, so maximum likelihood ideas and so forth. Um, it'll be due 2 weeks from Friday, so I try to give you up to 2 weeks to do the homework, but with homework one being due this Friday, I didn't want to assign this homework simultaneous to having homework one out. So I pushed the assignment date till Monday. So I hope that works. And again, when you see it, again, we'll talk about a little bit about it at the beginning of class next time. But I also wanted to make sure that we can talk, that you know that any questions you have, I welcome them over email, office hours, or otherwise. Just get a hold of me if you have some questions. Okay. All right. Any questions for me before we start today's fun? I'll put it in fun. Maximum likelihood really is fun. Okay. No questions. I will move forward. So I'm going to start by describing. Oh, Vladimir, yes, question. Yes. Yes. Yeah, it's that awkward part. The question was, could I rephrase the questions? And the answer is yes, and I will try to bit better at that. I want to make sure that your likeness and image and sound are not on the internet. So that is why I've muted the audio from you so that you can feel comfortable in asking me any questions that you need. But I will do a better job. I apologize for that. Thank you. Other questions? All right. You know what's really funny about this, just speaking, I'm I can tell I'm getting into teaching voice mode. I know I'm loud. I'm really loud. And I don't have to be that way because my headphones are like where this is and I can hear it. I feel bad for Lisa and my son Hugh because they're hearing me shout from the basement. And it's just like this automatic. I don't know if you ever get in that mode where like I'm teaching and it's just the volume that comes out. So I'll try my best to like, let's talk about maximum likelihood in the calm way. But there's nothing calm about maximum likelihood. It's really hard for me to calm down. So I apologize for that too. All right. I wanted to start though. Akyung, you had a question last week about how we derive the true version of the semi-partial correlation, and I did create some information about that. Um, Gotta find out where I put it. It is in our lecture '01 files on GitHub. There's a R Markdown file, and if you find that, and I know my screen's a bit small, so let me zoom that. Can you observe, can you see things okay on the screen in terms of font? We're okay. Okay. So I wanted to show you the derivation because actually how I derived what the true value should be fits into what we talked about last week. And if you remember what we talked about last week, we talked a little bit about algebra of expectations, right? How we derive expected values, variances. Well, covariance actually falls into that too. So this is an example, and it reinforces what we did last time. Shall I go through it? Sound good? Okay. You'll recall this syntax I added to describe how to look at semi-partial correlations. And so I created a data set. Now what I've done is created a very large sample size in my data set, like 10 million observations. The reason for that is as the sample size goes up to infinity, our simulated data should give us the true value. Like sampling error should be reduced. Last time, I don't remember, I think I like 100 observations where sampling error might be large. So I wanted to come up with enough numbers here so that I could take how I generated the data, derive what the true correlation should be, and then check it with the example. Sound good? Okay. So again, I generated y from a normal distribution. I generated x1 and x2 from a normal distribution. And you'll note here, this is a weird simulation in that y, x1, and x2 not correlated, independent of each other. Right? So if you predicted y from x1 or x2, you wouldn't find anything. But the auxiliary variable right here is what I generated as a function of y, x1, and x2. Right? So now my auxiliary variable is related to each of those. So that means if you were to think about it, um, it's sort of your intermediate between the x1, x2, and y as well. So if we wanted to look at this, here's our auxiliary variable equation. These are the weights I use: 0.05 times y, zero point 0.5 times x, zero point 0.3 times x2, sorry, x1 times 0.5, 0.3 times x2. And then I generated the standard deviation of error to be 2 in that sense. So if we wanted the total correlation, the result that we really have to think about is a correlation is a covariance divided by the standard deviation of the product of the standard deviations of each variables, right? You may remember that from early statistics. I didn't cover it much from the mathematical stat sense, but this formula is one of the classic intro math stat formulas you're going to find. And we can use algebra of expectations to tell us what the variance of the total variance of auxiliary variable is. If you remember from last week's class, a constant times a random variable, the constant squared comes out, right? So we apply this var function across each of, I don't know why I opened a dictionary there, each of our components of the linear model. You'll note the following. So if you work the math through, you'll see that the variance of the auxiliary variable is 12.75. And if we wanted the just non-semi-partial correlation between y and auxiliary, I know we're working our way to just semi-partial, but we're going to get there. The correlation between y and auxiliary, we start with the covariance, right? The covariance of y and auxiliary, we have to go back to this model equation as well. Actually, this substituting in y with auxiliary. And what you'll see is that what we get from that, the only thing common to the model for auxiliary and the model for y, there actually isn't a model for y, or there is, it's just implied by following a normal distribution. So here, when we plug in those models, what we're left with is the coefficient that multiplies the y term times the variance of y, and the variance of y is what we set right here as well too. And did I make a mistake? No, that's right. Variance of y, standard deviation was 10, so the variance of y is 100. So that tells us the covariance between y and auxiliary is 5. How are we doing so far? Okay, so the total Pearson correlation is that covariance of 5 divided by the product of the standard deviations. So in this case, 5 divided by the square root of 12.75 times 10. That square root function should be across the entire 12.75. Actually, 10, no, it was 100 up here, so that's right. 12.75 is the square root. So that works out to be about 0.14. Okay, so that's the true correlation between y and auxiliary. If we really wanted to take a look at what that happened to be, let's see if I can generate it here. Core of y AUX, it's right about that 0.14 also. So you see that the result is confirmed in this simulation here, or mostly confirmed. So then we have to compute the semi-partial. And remember, the semi-partial correlation is where we take the auxiliary variable and we take its residual, or what's left over from it, and correlate it with y itself, right? And in this case, what you'll see is the regression, we can come up with a predicted value of y of auxiliary based on our true value of our function, x1, zero point 0.5 times x1 plus zero point 0.3 times x2. The variance of this predicted part, we could calculate also using the methods we just described. So the variance of auxiliary is 8.5. And then if we wanted to look at what is the residual variance, right? It's the difference between the variance of auxiliary and the variance of auxiliary once it's been predicted, right? This is almost like how much we've explained in variance. So it's 4.25. So here what you'll see is now what we're after is the semi-partial correlation. This notation I may have messed up just slightly. This should really be the residual auxiliary. Or another way of putting it is that term right there. Actually, no, this is the covariance between y and auxiliary, but we divide it by sigma squared times the standard deviation of it. And so in that case, what you'll see is that gives us about 0.243. That's our final answer. And you'll see that's the number that we received there. So how did that do? How did that work for you? Any questions on any of that? I will say it's not direct. And in generating the data, this part right here, that was an interesting process, right? So um, there are all sorts of ways of generating data. You could start with a correlation, just a multivariate normal amongst four variables. But in this case, I just started trying to build it into a model-based framework, and that's how it works. So auxiliary variables, what we're going to see next week is how to incorporate them into maximum likelihood algorithms, which helps with missing data. This week's homework, as you know, you're looking at correlations and semi-partial correlations of auxiliary variables and an outcome or missing data to see if that auxiliary variable might be somehow related to it. Now, I note that the homework is not exactly the most ideal method because missing data exists in it still, and Pearson correlations are sort of messy. The book talked about a latent variable method, but I thought this was something we could do based on either what you should have known from other classes or things I could teach you right away. And that's where we started with it. But any questions on any of this before I move on to the lecture? No. Okay. Well, there you have it. I hope that helps. Oh, question. Yes. I hear somebody. No. All right. Let's keep going then. All right. Let me move back to the folder I was in. I have some example R script here. And I have a lecture on maximum likelihood estimation. I noted this is not online net lecture number 6, and this is bad on me. That's where the class I taught it from was. How embarrassing. I'll have to fix that. Fix the title slide, Templin. I did work through the slides to make sure they're the right content, but I didn't look at the title. Come on, Jonathan. Sloppy. But I tell you, it is good. Last week we talked about distributions and linear combinations, algebra of expectations. So like a primer on mathematical statistics. This week, we're going to take what we learned last week and derive likelihood functions from them. My purpose in telling you this is to get you used to maximum likelihood if you're not, because the likelihood function is the key to handling missing data, not just in maximum likelihood, but that same likelihood function shows up in Bayesian statistics as well too. So spending extra time on maximum likelihood and how it works, to me, is important to try to get ourselves in the mindset for how we approach most problems with missing data, or try to frame most problems is when we get to Bayesian and missing data or multiple imputations we go forth as well. And this is, remember, there were three methods that Enders talks about with respect to missing data handling, trying to achieve the assumption of missing at random. Those methods were maximum likelihood, Bayesian, and multiple imputation. And each of those, though, sort of in the first case, the first two, maximum likelihood absolutely depends upon a likelihood function. Bayesian actually depends upon the same likelihood function augmented by prior distributions. And then it turns out multiple imputation takes a different approach, but it's somewhat equivalent to building a model with a likelihood function as well. So I sort of look at the three as heavily related, intricately related. And perhaps the biggest difference that you're going to find in them would be the difference between maximum likelihood and Bayesian. Because it turns out you can do multiple imputation through Bayesian methods as well too, maximum likelihood or Bayesian as well too. So all sorts of relationships amongst the three different methods that we're going to dive into. So the basis of this lecture, we're going to cover the basics of maximum likelihood. It's the I will say it's the engine that drives most modern statistical methods. And by modern here, I'm talking about path analysis, structural equation models, item response models, uh, diagnostic models, mixed models, multi-level models. You want to keep going. So basically, maximum likelihood is an important part of statistics. It's interesting, as I started teaching this class, and I mentioned this to you last week, um, my version of this is sort of my version of multivariate statistics. I feel like we can't teach multivariate statistics in this day and age without talking about likelihoods. And I think that's missing a lot from what we end up having a lot of multivariate classes. Um, so not only am I going to talk about maximum likelihood, but maximum likelihood is everywhere, right? Why is it everywhere? Is part of the question I'm going to ask you. Think about that. And part of that reason is answered by what we get from it, right? So we get a series of very regular pieces of ways to look at results, right? So, for instance, if you're model building, right, in a linear regression sense, if you predict y by x, and you want to add z, right? So you want to compare a model with y being predicted by x and y being predicted by x and z, and you use maximum likelihood for it. There's a way that test whether the addition of z helps improve the model, and that test is called a likelihood ratio test. Well, that's a very basic example using multiple and simple linear regression, but that likelihood ratio test idea still applies whether you're in that basic simple linear regression example or you're in a path analysis or a multidimensional item response model. So likelihood ratio tests are your way of doing model comparisons, and they all come about because of likelihood theory, maximum likelihood theory. So it's really a great procedure to get familiar with because what you do in statistics with it is so common. Similarly, some things called Wald tests. You've already used things that are like Wald tests. If you looked at your coefficients table from a linear regression, the Wald test would be the standard error or the coefficient divided by the standard error. And that, in a maximum likelihood, strict maximum likelihood sense, that forms a statistic that should converge to a normal distribution. So that's how we can build that. Well, the nice thing is why that's the case is, again, likelihood theory. So likelihood theory permeates so many places. And then there's also likelihood theory based criteria. We call them information criteria, again, used for model selection. Um, I can go on and on and on. And actually, there's another thing I didn't mention here. It's something called the score test. So maximum likelihood is not only good for estimating a model, but it's also estimating multiple models that are nested. There are a series of results that built that in, and that's why you see a lot of uh, model-based approaches that build from kind of an incremental analysis approach, where you're adding variables and continuing in such a way. And then, so again, most of this lecture, maximum likelihood could be a lecture we give with no examples whatsoever, but I hate that. We're in applied statistics class. And if you're like me, when I learned this, I can only learn so much from the symbols. I have to go and see it in practice. And so what I'm going to do is talk about maximum likelihood from a theoretical perspective to begin with, but then move to apply what we know, what I talked about, in the context of general linear models. So I'm going to introduce a couple different packages today. The NLME package for nonlinear mixed effects, and LME for linear mixed effects in R. We'll also talk about Lavaan, although next week will be much heavier into Lavaan for what we do. I mentioned Lavaan before. I showed the result from it in the first lecture, I believe. So, questions or comments about anything before we begin? All right. And while I claim to be a Bayesian, sort of, I will say I'm a likelihoodist. I like the likelihood theory the best, and that shows up in Bayes as well too. So this is pretty cool stuff. All right. Do you remember the data we talked about last week? We had this actually a couple weeks ago. The employer trying to hire employees for a job where something called IQ is important. Again, I don't believe in uh, there's one factor of IQ that really does everything. But this is a simple example, so we're going to run with it. I'm only going to show 5 observations from this data set, and I'm going to show the complete data for it because I want to show how the math for maximum likelihood works, and it's a small enough number where we can play with it, the data. Right? So I have these 5 observations. By the way, I'm not making any inferences off of this. I'm just doing this to demonstrate how maximum likelihood works. Like if you have a sample of 20 and you pull out 5 observations, first of all, sample of 20, probably not enough to describe a meaningful trend that generalizes. Sample of 5 from that, definitely not enough. So, but this will help us as we go forward. Keep in mind the descriptive statistics. The average IQ here is 114.4. Uh, average performance is 12.8, standard deviation of each here, and you have a covariance matrix below as well too, between the two. So let's talk about estimation. How many of you like doing estimation? I know. I'm wired differently. All right. I get it. Thank you, Farhan. Um, like you, when I was in grad school, I just wanted to know how stuff worked. Like if you look at a car, I'd be the guy opening up the hood and trying to figure out how the engine ran, right? And that's how I felt with me learning maximum likelihood. So estimation is really what we're after. And maximum likelihood is one type of estimation, but you've heard otherwise. And this is a really rough guide to how estimation works, right? We can minimize something. What's the something? Oh, well, we have to define it, right? Usually we call it a loss function. We want to minimize loss of some sort. This is typically found with names that have least in the title, right? So forms of least squares, generalized least squares. How many of you have heard of generalized least squares? Or ordinary least squares? That makes it sound so sad. It's just ordinary. It's not generalized, right? I wish they would have called it plain least squares. That would be much more accurate. Weighted least squares. Anybody heard of that? About diagonally weighted least squares? Weighted least squares mean invariance transformation or WLSMV. Anybody heard of that? Here's another one. Iteratively related least squares. Each of these is an estimation method. Iteratively reweighted is sort of how we get generalized linear models like logistic regressions real quick. So the GLM package in R, function in R does that. I call this the estimator of last resort. We're going to talk about, well, I'll talk about why for a second, but the idea again is you define a loss function. So in ordinary or just simple old least squares, like a linear regression, our loss function is the square distance from the outcome y to its predicted value, given by a series of coefficients plus predictors, right? We square that, we sum it over all the observations, and we try to minimize that. That's our loss function. And it's loss because literally we want to minimize as much squared error as there is possible in our sample, right? It's the estimator of last resort often because in these systems, the loss function doesn't usually involve a likelihood. And the likelihood function is the thing that has some really important properties in statistics. And so when I say it's the estimator of last resort, you might be thinking, well, I use least squares for all my linear models, like linear regression. Yes, it turns out in that case, your ordinary least squares gives you the same result you would get to maximum likelihood, but only if you have complete data. If you don't have complete data, it's not the same result. So, yes, last resort, I guess I should qualify that to say, except for when it's equivalent to maximum likelihood with complete data. So, ordinary, also iteratively relate we rate or generalized least squares, iteratively reweighted least squares. Those all have an equivalence with maximum likelihood. There's this. Well, I don't need to go in that struggle that thing. So we do use this, but that's one method of estimation. Second method of estimation is maximize something, right? So clearly, we had a function here we're trying to seek the minimum. That's why we call it a loss function. We want to minimize loss. Maximize, that's a different idea, right? So this is where we find maximum likelihood. That's where maximum just shows up in the title, right? So forms include maximum likelihood, ML, short for maximum likelihood, residual maximum likelihood, which you may have heard of if you've taken a mixed model or multi-level model class before, sometimes called restricted maximum likelihood. There's also robust maximum likelihood, which Enders talks about as well too. And I will say that these estimators are the gold standards. And anything that uses that likelihood function. So basically the idea is this: before we built a loss function and we sought to find its minimum, and finding its minimum we can do through calculus or numeric methods. Numeric methods means we use the computer. Calculus, if there's a closed form, means we have a formula for it, but we have to use calculus to figure out what that formula is. I'll show you in just a moment. So maximum is the opposite, right? Instead of finding a minimum, we just flip the function over, and it relies upon, to maximize a likelihood, relies upon something called a likelihood function. We want to maximize the likelihood of. So it's sort of a flip. The process, though, still maintains. We can find the maximum of a function using methods that were taught in calculus. If you haven't taken calculus, don't worry. I'm not going to make you do any calculus methods. What the concept of the methods is much more important than the actual doing of the methods. And that's what I'm going to talk about. So that's maximize something. Any question about minimize or maximize? No questions. All right. Finally, the last way that we can estimate something is, again, these are broad classes, and you could probably come up with ways that aren't part of this, but my taxonomy for now. We can use simulation to sample from something, right? We could basically simulate from a function, and based on the simulation values, we could pull estimates from them. This is, I would say, more recent in terms of when methodology became widely used. And sampling approaches, names include Bayesian, Markov chain, Monte Carlo. Turns out all Markov chain Monte Carlo is Bayesian, so just a heads up. But not all Bayesian is Markov chain Monte Carlo. That's a little weird too. Gibbs sampling, Metropolis Hastings, Metropolis algorithm, sometimes shortened to Monte Carlo if you're in a physical science like physics or chemistry. I could add to that Hamiltonian Monte Carlo or hybrid Monte Carlo. There's all sorts of different words. I would say that Bayesian can be used for complex models where ML is not available, or for methods where prior values are needed. So if you have a prior belief about statistics. Now, ironically, these three methods can essentially map into the three methods that we talk about for handling missing at random data, right? We know already that maximum likelihood is one of those methods. So it turns out this maximize, as long as it's a likelihood function, is one of those methods. Turns out sampling, simulation, well, anything from Markov chain is Bayesian. So this is your Bayesian perspective. You don't always have to use a Markov chain, but I'm not getting the. If you want to know the details of that, I'll be happy to answer a question, but that doesn't need to be in the middle right now. But sampling, that's Bayesian. But it turns out you can actually use least squares methods and get protection from missing data, or try to get to a missing at random assumption when you use multiple imputation. So what you'll see is we're going to talk about a package called MICE for multiple imputation. It's called multiple imputation by chained equations. If you don't tell it otherwise, it literally runs your data using ordinary least squares, a series of ordinary least squares. And at the end of it, you have a bunch of data sets that are complete based on the missing data process that then you can go run through even least squares estimators. So there's this interesting combination of how we estimate models and how we assume certain features about missing data as we go forward. How are we doing on all this? You can see why I love this topic. It is so amazing. I know it's sarcasm, but maybe you can substitute just laugh at my enthusiasm. Like you can laugh at my enthusiasm. Maybe does that sound good? Okay. Or maybe I just need some gimmicks in my slides, like some explosions or pictures of cats or something like that. I don't know. I'm not good at that. Not good at a lot of things. All right. Let's get into an introduction to ML. Um, so, first things first, why we use maximum likelihood is because assuming some assumptions are met. Now, in statistics, these set of assumptions, they don't even call them assumptions, they call them regularity conditions. How about that for some jargon? Yeah. Well, did you meet your regularity conditions? I don't know where you're going with that, right? Assumption, I'll take, but most data tend to meet those assumptions, I'll say. We'd like to believe it at least. But if you do, then you get these good statistical properties, something called asymptotic consistency. Now, you're going to see the word asymptotic before. That's a technical term. Think of an asymptote, right? An asymptote of a line, where a line may eventually, as the line, you can think of a curve. It asymptotes at a value. If you could see where infinity was, it reaches that value, but no above it, right? That's what an asymptote is. In the context of maximum likelihood, when we talk about asymptotic, we're talking about the behavior of the statistics that you're estimating as n goes to infinity. And that n going to infinity is really the key in thinking about why maximum likelihood works well, right? So as n goes to infinity, asymptotic consistency notes that the estimator converges in probability to its true value. So again, if you meet the assumptions of maximum likelihood, um, then as your sample size grows, you have the understanding that the values of your point estimates, of your parameters, should converge, again, in probability, which means that probability goes to 1 as n goes to infinity, to their true values. And you can even think about this when it comes to, well, I'll talk about that in just a bit. So that's good, right? That means you get enough data, you're going to be pretty close to what the true values of parameters are. Sign me up. I'd like that. Wouldn't that work? Why would we do statistics otherwise, right? Well, in this model, you may not get the true values. What are you talking about, right? Okay. Second, asymptotic normality. So as that sample size increases, as n goes to infinity, the distribution of the estimator becomes normal. It converges in distribution to a normal distribution, right? And not only that, that normal distribution has a mean of the point estimate of the parameter and a variance given by something called an information matrix, or Fisher's information if you have a single value, right? This is calculatable. So that is where we get all sorts of information, right? Think about your linear regression coefficients that come out. You can see a point estimate, you get a coefficient, you get a standard error, right? So the standard error is the square root of this variance coming from an information matrix, right, for each of those coefficients. So that's where that comes from, right? There's nothing about a linear model that says what the distribution of the parameters should be, but if you use maximum likelihood, you can show what it would be as n goes to infinity. I think that's pretty cool, right? That also, if you think about your regression output, you get parameter point estimate, right? The coefficient, you get standard error, and there's usually another column, depending on the program that you use. If you're using R and LM, it's like a T value, right? Which is parameter divided by standard error, right? That forms a test statistic that we can build if this assumption holds, or it's based on this assumption that forms a test statistic. Now, the t value is a little bit more precise. It's sort of a finite sample version of it. Normally, we would call it a z value. And in fact, if you use M plus or Lavon for simple linear models, you won't see t, it'll say z there. But that z is from this normal asymptotic normal assumption. Pretty cool, huh? So we know that our parameters get to their true value. We also know as they're going to their true value what the distribution of the parameters should be, all based on likelihood theory. The last part of it is also nice, efficiency. It's been shown that no other estimator will have a smaller standard error than maximum likelihood. Now, there are cases like in Bayesian, like what we call a standard error, posterior standard deviations. We can trick a prior distribution to make those small or big. But in a comparable type of approach and model, the standard error will be smaller in maximum likelihood than any other estimator. That's also pretty cool, right? So that gives us smaller standard errors, means more power for our hypothesis test, right? How's this working? How's this work for you? Understandable? Questions? Yes. Question. Well, technically, yeah, actually, each of the standard errors may have standard errors as well, too. But no, I'm talking about the standard error just of the point estimate. So if you have a beta, like a linear regression, your beta coefficient will have a standard error to it. That standard error for beta will be smaller under maximum likelihood than any other method, is what's saying. Now, it turns out in linear regression, that example, least squares is equivalent to maximum likelihood, so they'll be the same. But there will be no other estimate will be smaller. It'll be equal to or smaller than. Does that make sense? Does that answer your question? And actually, I didn't rephrase your question. The question was whether we're talking about the estimate standard error or the standard error of the standard errors. And I believe it's, in this case, we're talking about just the estimate standard error itself. Okay. So, because maximum likelihood estimators, I will refer to those as MLEs, uh, have such nice and well understood properties, they permeate statistics. They're everywhere. If you only take like introduction or intermediate stat class, you wouldn't know it because we don't talk about them there. But sure enough, they're there, and they go in lots of places. So, other questions I should ask. Okay, no other questions. All right. So, maximum likelihood, the estimates themselves come from the statistical distributions. And we talked last week about the statistical distribution, right? Each random variable can be described with a PDF, a probability density function, particularly for continuous random variables. Um, the alternative is a probability mass function, which is usually using discrete random variables. We saw that last week. We're going to talk today about with the univariate normal distribution, but we'll quickly move to other ones as we go on. But for a single random variable x, that's our PDF of the normal distribution, right? And last week we said, let's assume we know what mu is, and let's assume we know what sigma squared is. Then for every x we plug in, we can tell its relative likelihood, right? How high the height of the curve is for a given value of x, right? That's great. That's how we introduce statistics distributions frequently. For maximum likelihood, though, if you think about what we're seeking to do, we've observed x. That's our data. We don't know mu or sigma. We're going to do the flip. We're going to say, hey, given our data, what's the mu or the mu and the sigma that maximize the likelihood, right? That provide the maximum. So that's the flip about maximum likelihood. Instead of thinking that the data are random, now we have to assume the data are random to begin, this distribution shows up. Maximum likelihood says, okay, you've observed the data. Let's go figure out the parameters that were the most likely in what you've observed. Does that make sense? It's the same function, or at least the same functions at the core. We actually have to build a likelihood function. The likelihood function is a little bit more complicated than this because what we assume in statistics is that x followed a normal distribution. We said last time it was individually and identically distributed. Remember that little tilde sign, x tilde n? That assumption, this is basically the distribution of one of our observations. We have a sample of n. We know they all look like this, but each x may be different. So we have to build a likelihood function that incorporates all of our data. Well, there's our heights, right? We saw that before. Okay, questions, comments, any of this? Okay. So let's take a look at this distribution values for the IQ variable, right? Let's assume that we know the mean and we know the variance. Now, these are the sample estimates from those five values that I showed you on the first slide. But for for the purposes of instruction here, just assume that's the true value. Okay? Um, in reality, we don't know what the true value is, but we have to think about that in building this. It helps the concept go a little bit better, right? So if those were the true values, right? Um, what we end up seeing here is if x were 114.4, again, this is the what we did last week. If we plug in x, knowing the mean's 114.4 and the variance is 5.29, the height of x, or the relative frequency of x, is 0.173, and the height of x being 110 is 0.028. And last week we just said, oh, that shows us that 114.4 is relatively more likely than a score of 110. That's all it's telling us, right? That's the distributional assumption, right? So that's reminding you from last week. Let's talk about constructing that likelihood function, right? So maximum likelihood, the word maximum implies we're finding the peak of a function, and the word likelihood is what we're finding the peak of, right? So technically we're building a likelihood function that we will then go and use either numeric methods like the computational on the computer or calculus to figure out where the peak should be, right? So a likelihood function provides the value of a likelihood, right? It looks very much like this, although it's not exactly this. It's very much like this um, for a set of parameters, right? And so where likelihood functions begin is with the PDF, right? Density functions get provided for each observation individually, right? So if this was our normal PDF, right? If we put a little I under X right here, what we would be saying is each of our X's follows a normal distribution. The mean and variance for each X is the same, but the value of X itself may differ from person to person, which is what we would expect in data. So that's the start. And the likelihood function for the entire sample is the function that gets used in the likelihood process, right? Because it doesn't do us any good. In fact, it's unidentified to figure out what the mean and the variance are for one observation, right? We have two unknowns. Let's just do it algebraically. There's two unknowns, mean and variance, and we have one x. But once we have a sample full of x's, we can build a likelihood function that's across the entire sample, and then we can use that in our estimation process itself. How are we doing? And I'm going to show examples in just a bit here. Okay, so yes, question. Great question. The question was, what's the scale of likelihood? Turns out the scale of likelihood depends on the family of distributions it's in. It's not necessarily 0 to 1. The likelihood itself cannot be negative, though, right? So you can think of the likelihood as sort of bounded between 0 and infinity. Um, what you're going to see is that each individual will contribute a portion to that likelihood itself, right? And I should say why it's 0 to infinity, you're going to see very quickly. But a likelihood function turns out is a product of PDFs. And if you think about these PDFs, there's nothing that says the PDF value needs to be like the actual height of the curve is bounded, except for it needs to be above 0, right? It's a relative frequency. So you can think of multiplying numbers that are somewhere between 0 and big. Now, in most of the models I'm going to show today, like a normal distribution, most of those values are between 0 and 1, so their product gets very, very small. But it's not necessarily the case, right? I could build if I shrunk the variance, for instance, of this normal distribution instead of zero point 0.2, if I made it 0.02, that peak would be above 1. Does that make sense? Thank you. So likelihoods themselves don't really have a great idea of what um, sorry, there's no real range except for they're positive. Let's put it that way. The positive numbers are 0 or above. All right. So again, the likelihood function is for the entire sample is used in this estimation process. It can be thought of as a joint distribution of all the observations simultaneously. Now, when I say joint distribution, we talked about that last time also, right? We said, oh, x and y, like if we put them both together, we have this joint distribution or of x and y together. And we talked about how that was related to a conditional times a marginal, and where y given x times f of x can give us back our joint. But the joint distribution concept is really thinking about this is a distribution that provides one likelihood for all the input values that go in. So for x and for y simultaneously in that two variable example. For us, the likelihood function is taking all of the data points, right? So everybody and building that in. So it's like a joint distribution for everybody. In univariate statistics, observations are often considered independent. So this joint likelihood for the product is constructed through the sample is constructed through a product. Do you remember last week when we talked about independence? We had the coin flip example, heads and tails for a dime, and was it penny? I think it was. I hear the penny's going away, or at least our new king wants to remove the penny. So the idea for that is um, that independence being a product of marginal distributions is what we use to build a likelihood function, right? So when we say our sample is independent and identically distributed, we could talk about how they vary jointly by multiplying their PDFs together. And that's where we're going to start. Right? Questions? We're going to start in 10 minutes. So let's take a break. I asked questions, but I cut that down. Any questions on this? Let me just ask that for a second. Just know that your question is standing between us and 10 minutes of break. I'm just kidding. I can ask that question if you have questions when we get back. Take a think about it. Think about it. I'll shut down for 10 minutes. If you don't see my video or audio on, you know that I'm away from the computer, but I'll be back and have that on when we're ready. See you at about 1:30. Okay? Thank you. Okay. So any questions on any of this so far? Likelihoods, sample likelihoods, building a function. Okay. Okay. All right, so let's think about a likelihood function for one observation. This is a really bad idea. I mentioned just a moment ago it's unidentified, but we're going to do this anyway because it's the start, because the process is easy to visualize with one, not as easy to visualize when you have more than one. So let's assume the following. We have observed the first value of IQ. So that data set that was in the first couple slides, we'll say X is 112. We're going to assume that IQ follows a normal distribution. And that the variance of x is known to be 5.29. Okay, I have to do the variance because as you see, there's two unknowns, and I'm only going to have one piece of data here, x. So what we're going to be able to do is what we need to do is figure out mu. That's our whole goal from this small example. Now, a couple other parts of that. X follows a normal distribution. Why would I just assume that? It's like one of those, it's the thing I always felt like in the theoretical classes. Well, I just assume X follows a normal distribution. The end. Well, it turns out our likelihood function really is built by the distribution assumptions of the models that we built, right? And we talked last week about what we assume about y in a linear model, right? We assume it's conditionally normal, conditional on the values of the predictors. So that's the information we'd know to say, oh, because of the structure of our model, y has to follow a normal distribution. And that's what we use to sort of build our likelihood function with, where we started with. Now, you may be thinking to yourself, I'm not going to be able to do this or need to do this, and probably not. But there are some methods, particularly the factorization method in maximum likelihood that Enders talks about, where you may want to do this. And so knowing about your model is your first step to understanding which distribution to use. And then from there, it's a matter of doing the process I'm about to show you. But for us, again, because we only have x, and we have three unknowns in this equation, and we're going to solve for one of them, right? We have to know two of them. Well, we observed x at 112, and let's just assume that we're clairvoyant, and we know that the variance is 5.29. Perfect. Sounds good. In practice, we'd never do that because, and this is why this is sort of a bad idea, like we can't assume what the variance is. That doesn't make any sense, right? what we need is more x's to be able to figure out what the variance is. And you can think about that. Remember the variance formula, if you divide it by n minus 1 and you have one observation, now you're dividing by 0. And the math joke I try to make here, and really badly, is I believe in mathematics we say dividing by 0 is undefined. That kind of seems like it's that's a little dissatisfying, isn't it? Like how long have we been a species that studied math, and we're going to be like, yeah, undefined, whatever. Anyway, they're like, if you think about that in language, like there are so many words in like the Words with Friend app that I have no definition for, but we can play them, and yet we still can't divide by 0. Come on now. Anyway, I digress. I'm trying to make this a little more entertaining than just straight statistics. So this is our PDF. We know x, that's 112. We know sigma squared, that's 5.29. We got to figure out what mu is, right? So if we do that, we plug those into the formula. And now for every value of that mu could be, this likelihood function now returns a number that tells us how likely mu is, right? So before, remember, we plugged in, we knew what mu and sigma were, and we plugged in a given x. This is flipping it. We're saying we know what x is, and actually we know what sigma is. Tell me how likely mu is that led to that x. What's the mean that would have led to that piece of data, right? So the actual value, the actual height, is not yet relevant. It's the value of mu at the height that we're after. So the value of mu with the highest likelihood is called the maximum likelihood estimate. Now, note the subtle shift in language I used. In the PDF language, I said you plug in X and you get the relative frequency back, right? Here, what we're saying is you plug in mu and you get the likelihood back, right? And the shift is because of what's being put in, right? Data, we like to think of as being random of some sort. So that's why relative frequency is used. Mu, we're talking about likelihood based on how likely that mu, that's the mean that gave rise to our data, right? So rather than saying it's relative frequency of mu, no, there is a mean. We have to believe there is a mean that gave rise to our data to use this model. And this is the most likely value of that mean, is what it's saying, right? So that language shifts subtly, but that's the importance of it. Where I said from the PDF, it's a relative frequency, but what that refers to data. When you plug in data to the function, you get a relative frequency out. When you plug in a parameter to the function, you get a likelihood out. Sound good? Okay. All right. So let me just ask a real rough question. For this likelihood, what do you think the MLE would be for mu? What's our most likely mu value here? It's pretty, yeah, what's the most likely mean? Uh, from the chat, data itself, correct, right? So conceptually, you can think of what's the mean of one observation? The mean, but that assumes that you knew the mean formula, right? The sum of x over n is the mean. That's what we're trying to figure out for maximum likelihood. And you're right, it is the mean. It's 112. But looking at this function, what's the value of mu that maximizes is what you'd have to say. And to see that, you'd have to see that when you plug in 112, the numerator here goes to 0. So this exponent raised to 0 is a value of 1, right? So just leaving this, what we call the normalization constant on the outside. And any other value that we plug into that exponent will be a value that's lower than 1, meaning that it has to be lower than the mean. That's one way of looking at it mathematically. But let's look at it with data, right? Turns out 112 does provide the highest likelihood is 117.3, right? So the way that we notate this is the value of mu x, that's our parameter, that maximizes our likelihood function of mu conditional on the data and the variance, right? This is what we knew to plug into the formula is 112. Okay? Sound good? One observation, not the most interesting. Now let's build the sample likelihood. Okay? So we have one observation, but we weren't working with a sample, so we have to assume some things about the sample. And we're going to assume, again, our observations are independent and identically distributed. Because with that assumption, we have a very clear idea of what to do with each observation's PDF, right? So what that means is independent means we can use a product. Identically distributed means each of the things that we're multiplying will have the same PDF form, meaning it has the same mean and the same variance and the same distribution, really, right? Same distribution, same parameters. So that means our likelihood function for mu and sigma squared, now we want to find both of those, conditional on all of our data, x1 through xn, if we have a sample size of n, is the product of likelihood functions for each observation itself, right? So that product we can express with this capital pi. So the product from person 1 to n, that p is for person, that's for each observation in our sample, is their PDF with xp put into the PDF itself. So if you go back to the normal PDF, right here, we're going to put the little subscript p on x to refer to that's person p's value of x. Okay? So then we get to the ugly math. I mean, I don't know about you, the product is ugly, but it gets really ugly when we start doing a product of all this exponents, radicals, things like that, right? Ugly. But let's parse through it. We substituted f of x with its PDF, and then here we have our p value, right? So this is literally taking, if we were to plug in a mean and a sigma for each person, that'd be like going back to each person's normal distribution function and calculating the value for that mean and sigma, conditional on us knowing what a person's data are, right? So it's another height, right? So here's our height. So that's our product. Now, this is a normal distribution. This right here might be, if you were doing this with other distributions, you might just stop right here because sometimes factoring it is very difficult. But I'm going to go factor it through a little bit, do a little algebra. And I'm not expecting you to do this, by the way. None of this is for you. This is just for demonstration purposes, right? So just turn, if you're like me and rusty on algebra, turn the algebra brain off and just observe and just pretend that I'm telling you something that you have to believe. Sound good? And if you need to confirm it, oh, don't go to Chat GPT. Maybe you should go to Chat GPT. I don't know. Oh, another story on that for another day. What do we do here? All right, the product, turns out the product of this term in the front, if you remember the product of fractions, right? We could express this fraction as really 2 pi sigma squared for any one case raised to the negative 1/2 power. Well, that thing n times really means we have n in the exponent. So this normalizing constant is 2 pi sigma squared raised to the negative n over 2. Okay, so far? And if you remember your rules of exponents, which I don't, I have to look them up, just to be real. But if you do, you'd know that when we take a product, remember E is just it's a constant, 2.71, Euler's number. So it's raised to a product. And similarly, before we added up all the n to get n here, we can take the sum of the terms in the exponent to get that E there. Okay? So this is what we would call our likelihood function. The term that's down here where you don't see the product is equivalent to the term just before it. It's just with algebra to sort of rearrange things. And if you're familiar with where we're headed, you know why in just a bit. How are we doing? Sound okay? But what you can tell with this is that now, instead of dealing with one x, we have a place to deal with all of the x's in our sample, right? This function is a function of mu and sigma squared. We've observed x. For any combination of mu and sigma squared we plug into this function, along with us observing x, we now get a likelihood for each of mu and for each pair of mu and sigma squared. Cool? Okay. So from that previous slide, there's that right there. For this function, there's one mean, one variance, and all of the data. As I mentioned before, if we observe the data but do not know the mean or variance, we call this a sample likelihood function. So rather than providing the height of the curve at any value of x, it's giving us the height of the curve, which we call the likelihood, for any possible values of those parameters, mu and sigma squared. So it's up for now. The question for us is how do we figure out where the maximum value happens to be? Sound good? By the way, let's stop for a second and think about this product. If our observations were not independent, we wouldn't be able to do the product. We'd have to go and reconsider what we're doing. Uh, we may make a product of multivariate normal distributions, for instance, in which case that's what happens in multi-level models, right? You may have dependencies within cluster or dependencies within time, within person, something along those lines. So that sort of violates independent and identically distributed from a normal perspective, from a univariate normal, but there are other distributions that we can adapt to fit that to build it. So a lot of different places for what we do. Okay, so if we take our likelihood function across all 5 observations, imagine that we know, again, sigma squared x is 5.29, but we don't know the mean. I'm showing you this, imagining this, because now I can plot it in 2 dimensions, right? If I didn't know mu and sigma squares, that's a 3-dimensional cube, which we'll get to, but not right now. Okay? The likelihood function gives us a range of values for mu of x, right? So literally in R, I just plotted values, and it turns out the maximum value is at 114.4, right? So the maximum with respect to mu is, turns out that's our sample mean. And the height of the curve is 1.67 with 6 zeros in front of it. Really infinitesimally small. And that's because this likelihood function is a product of normal distributions. And those normal distributions likely have values of heights that are between 0 and 1. So we're multiplying 5 numbers between 0 and 1. It's getting smaller and smaller and smaller. Remember, it's not always the case that that's that. So, questions on any of this? So what I would say is 114.4 is our maximum likelihood estimate of mu, right there. Okay? Now, more often than not, we don't work with likelihood functions. We work with the log likelihood. And in part, that's 2 reasons, right? One is theoretical math. This function right here is really difficult to work with, but it becomes much simpler if we take its log. In particular, like we're going to see, to find a maximum in calculus, we have to basically differentiate this function with respect to the parameter of interest, right? So we have to figure out, and then we have to figure out where the slope of that derivative. Remember, a derivative is a line that's tangent to the curve, right? So if you were to think of a line, we want a line that has a slope of 0 that indicates either a maximum or a minimum. In our case, the shape of this function should indicate there's only a maximum possible. There's no minimum value listed. So here, working with exponents to do differentiation is a lot more difficult analytically, like if you're deriving this symbolically. So instead, we can take the log, and the value that comes from the log likelihood is a little bit easier to work with analytically using calculus. That's reason number 1. Reason number 2 is this. Look how small this number is right there. Right? That's a sample of 5 observations. What if I had 50 observations? Right? This would be getting smaller and smaller and smaller. Well, it turns out there's only so small of a number a computer can actually hold. Right? In R, if you'd like to find that, you can actually do type machine dot machine and put a $sign, and you could say double x min. That's the smallest number that R can hold. It's very small. It's orders of magnitude smaller than our likelihood happens to be. But as we get closer to this, rounding error has a bigger like every calculation in the computer has a bit of rounding error with floating point numbers. Numerical imprecision is what we call it. That error is exacerbated. So often what we do, the 2 reasons for why we use a log likelihood, one is if we are going to do some calculus on it, it's usually easier to work with. And 2 is if we're going to do it within the computer, it's usually more stable. Cool? All right. But when we take the log of the likelihood function, that doesn't change where the maximum is, right? So if we were to take the log of our likelihood function, what would change is not the shape of this curve or the value of x that provides a maximum. What changes is the scale of the y-axis, right? So in that case, if I took the log likelihood, you'll see the maximum is still at 114.4, but the log of that really infinitesimally small number turns out to be negative 13.3. So that's a much more easy number to talk about, I think. How are we doing? All right. What about the variance? Well, we assumed up to this point that the variance was known. I don't know about you, but I haven't run any model where I'm like, yeah, the variance is known. Let's run that. Anybody ever done that on real data? Been like, yeah, the variance is 3. End of story. Right? Again, one of those thought exercises to try to introduce it that we'd never do. Let's talk about this jointly estimating the variance and mean at the same time. Because we can use the same likelihood function or log likelihood function, right? The variance now becomes a parameter in the model, right? A parameter meaning another dimension that we'd have to search over. And the likelihood function itself is now with respect to 2 dimensions, right? Each unknown parameter is a dimension of that likelihood function. And so in this sense, we can take our log likelihood right here. This is our log likelihood function. Now, instead of just plugging in mu, we plug in mu and sigma squared, and we get a surface, right? This plot right here, the mean values, the parameter we're trying for the mean is along this axis, this diagonal axis here. The variance is along this diagonal axis here where my mouse is moving. Maybe I should change this to a pointer. Nope, that's not what I want. Laser pointer. There we go. Right here, that thing. And the height of this distribution is the log likelihood. Now, this distribution is really interesting. There's a big ridge on the top of it, right? So finding the MLE for the variance is a bit harder for this function. Look at the mean, though. The mean is nice and peaked. And the mean, if we rotated this cube and only looked at the mean, it would be looking like the peak of it would look like this plot right here. But if you look at the variance, it has a very small peak, if there's a peak at all, right? We'll talk a little bit more about that in just a slide. But here, turns out the maximum value of the variance happened to be 4.24. And this plot on the right is, if we were to use a contour plot, I think you saw contour plots in Ender's book. Sort of, if we flew over the top of the distribution, this is, lines are equivalent heights, right? You'll see the mean is right here, and then 4.24 is there. It's hard to see the variance. Now, the problem with that is why it's so flat is this is sort of telling, we're going to talk about curvature in just a moment, right? It tells us sort of a little bit of how much information, how confident we are that's really the peak, right? In the mean, we're pretty confident. That likelihood falls off pretty quickly when we vary the mean. But for the variance, it's hard to even see how much it falls off. So remember that for just a moment. The curvature at the peak is going to tell us something. But another question I have for you is, our MLE of the variance is 4.24. If you remember, not that I remembered, but it's prompting me here. On slide 3, we said it was 5.29. And do you want to know why that's the case? Because in the maximum likelihood estimate, the MLE for the variance uses the formula where we divide by n. Whereas in our sample variance that I showed you on slide 3, that divided by n minus 1. So the MLE for the variance, turns out there is a well-known bias in our MLE, meaning that as n goes to, we have to get to infinity before the bias goes away effectively. So for small sample sizes, the difference between the MLE and our sample variance is quite large. We would call 5.29 our unbiased estimate of the variance. 4.24 is our ML estimate of the variance. And again, as n goes to infinity, these two will converge to one value. How are we doing? Okay. So the process for finding the values for mu and sigma squared um, is kind of complicated. And what I just showed you before, you've read about in the book, because I asked you a question about it. This is a grid search. I literally plugged in a bunch of values for the mean, plugged in a bunch of values for the variance. There it is. And if, by the way, if you wanted to play along with that in my R code, you should be able to do the same, although I'm not playing with it here. You can play around with it as well too if you'd like to. Um, but for relatively, and I put this relatively simple functions though, we can use calculus to figure out what values of mu and sigma squared give us the maximum, and they're going to be fairly understandable pretty soon. Um, why I say relatively simple functions is not all functions we can do this for. We can't use calculus for every single one, right? Um, sometimes if we can use calculus and come up with a single formula, like a formula for the mean, the sum of x over n, we call that a closed form solution. Sum of x over n is the MLE. You don't have to go and do a grid search. You don't have to use other methods. But for a lot of what we do, there is no closed form solution. And so we have to use more efficient methods of doing a grid, like a more efficient grid search. A grid search is completely inefficient, right? We're just varying the mean, varying the variance, and checking values of any pair. Whereas we might be able to come up with calculus terms using small variants of it in our computational process. So those efficient methods, sometimes we call one of those is Newton-Raphson, basically using properties of the likelihood curve to figure out where the top is. How are we doing? All right. Well, I'm going to show you the calculus method first because it turns out in this example, we do have closed forms. Forgive my formatting here, but the calculus method to find the maximum makes use of the first derivative, right? So in our case, this likelihood function right here is a likelihood function of two parameters, mu and sigma squared. And really, if we want to figure out the maximum likelihood estimate for mu, we have to take the first derivative of this with respect to mu. Sometimes we call that the first partial derivative, right? And again, the derivative provides a line, the slope of a line that's tangent to our curve, right? So what we really want to do is figure out where the derivative is equal to zero. So if we could do the calculus and then set that first derivative equal to zero, we could then potentially solve for the parameter and figure out what the parameter estimate should be that maximizes it, right? Now, as I mentioned, the slope of a line being flat, being zero, from calculus can indicate we're at a minimum or we're at a maximum. But it turns out our likelihood functions are convex, right? The invert like a this is a concave function, this is a convex function, like a u, right? So a convex function has a maximum with no minimum. A concave function has a minimum with no maximum. Turns out we're protected here. Most of our functions that we look at are inverted U's, convex. Um, the other thing that we have to talk about, well, I'll get to that in just a bit. Sometimes there's more than one peak to them, although for most of the models we deal with, there's a single peak. But so the first derivative is the line that's tangent to the slope, and I grabbed this from Wikipedia. But here, if this is just a straight function, the blue line is the original function. It's x times the sine of x squared plus 1. It's a Wikipedia entry about derivatives, but I like the picture, right? So it turns out doing calculus on it, and again, I'm not requiring you to do that, but differentiating this function, taking the derivative of this function with respect to x, gives us a function that's the sine of x squared plus 2x squared times the cosine. If you're like me, you're thinking back to your calculus classes, if you took any, and you're like, oh my God, I would fail that class. Yes, I would fail that class if I were taking it right now. So I'm not teaching you the calculus because I don't know that I can, but the concept, right? And so what would happen is, and I can't get this graphic to play anymore. Uh, there it is, right here. what you see is that green line is the value of the first derivative at every part of x that you go on, right? So this line that you see moving is the slope of a line that's tangent. So that black dot that's moving along there is the point on which you're trying to find the slope of it. The slope of it's equal to the value coming back from the first derivative, right? And so if I back this up a few frames, we can see right here, that looks like a maximum, right? We call that a local, actually, this is the global maximum. There is no other maximum higher than that on this little section of the line, right? So we know, for instance, that this line will have a zero, the derivative will be equal to zero at this point right here. We also know it'll be equal to zero at this point and at this point over here too, right? Sort of multiple minimum, the value, like this little value right here, this other point, sometimes we call that a local maximum. This is an example of a function that has more than one uh, local maximum, because why I say that is the value of the derivative will be zero at this point right here as well too. And then you have to figure out which one is actually the maximum. But our functions work a little more better behaved. Questions on any of this so far? Again, please forgive my lack of calculus teaching expertise, but that's my version of calculus. Hooray. Turns out we can do that with our function too. And you can just take my word for it, but if we were to take our log likelihood function, this thing, and take the first derivative of it with respect to mu, well, first of all, in calculus, a derivative with respect to mu, if you don't have mu in a term, it goes to zero. So these constants out in front, or the function of the variance, goes away, and all we're left with is the term of the exponent here. And it turns out if we calculate the math for it, we actually get the following. This is our first derivative with respect to mu, right here. Now, if we set that equal to zero, right, we set this term equal to zero, right, we could multiply both sides by sigma squared, getting rid of it. We could then subtract n times mu x from one side, flip the equations around, then divide by n, and you get the point estimate. The value of mu that maximizes our likelihood function happens to be the sum of x over n. And I'm relieved, I don't know about you, but that's our sample mean. Isn't it nice to know the sample mean we've been calculating is actually our maximum likelihood estimate of the mean? I don't know. I feel relieved. Do you? Check mark. I like it. Thank you. Thanks for the check mark. I'm relieved. How about the variance? We do the same thing. Um, this gets really ugly. We've got a sigma squared to the fourth power here. Um, again, take my word for it. To figure out where the maximum is, we have to set this equation equal to zero and solve for sigma squared. When we do that, we can see that sigma squared is equal 1 over n times the sum of each observation minus its mean squared. Does that look familiar to you as a formula? So here, that's our variance. That's our MLE for the variance. So it turns out in very simple models like this is a ridiculously simple model, maximum likelihood estimates can be derived analytically using calculus. When I say analytically, that means calculus, right? We don't need a numeric solution. So questions on any of this while I take a drink? Okay, let's talk about the second derivative. All right. So um, we use our point estimates. We have the mean, we have the standard deviation or the variance. We can calculate those values, but we also want their standard errors, and the standard errors come from something called the information matrix. Right. The information matrix is the square root of -1 times the inverse matrix of second derivatives. So we have to take our result here, right? This is our partial derivative with respect to mu, right? And we have to integrate, we have to differentiate that one more time with respect to mu to get our information matrix out of it, this thing right here. Similarly, we have to differentiate this one more time with respect to sigma squared to get it as well. And so if we did that, if we take our variance of our sample mean, if we go up here and we take our first derivative of the likelihood function with respect to sample mean, and we differentiate that with respect to mu, take a look at what happens. If we distribute 1 over sigma squared through, the only term with mu in it is the very first term, which is negative n times mu over sigma squared. And if we do our derivative on that, the derivative of mu with respect to mu is just 1, so that goes away, leaving us with negative n over sigma squared, right? And remember, we need negative 1 times the inverse of that to give us our variance. So that leaves us with the variance of our sample mean is sigma squared over n. Anybody ever seen that before? Remember in basic stat, we talked about the sampling distribution of the mean? That's why it is what it is, right there. Right? That's the variance of the mean. Right? So the square root of this gives us the standard error of the mean, which would be the standard deviation over the square root of n. Remember that? How are we doing? Yes, question. They're not the same. No. Uh, Actually, let me do my matrix algebra is hazy. I actually think they would be equivalent, um, because. But let me back up. Let me just make the proclamation without proof that I believe they're equivalent. But I look at it as negative 1 times the inverse itself. So I take the inverse and multiply by negative 1. That's how I viewed it. All right. Other questions? You want to do this oh, I didn't do this for variance. Doing it for variance was very hard, but let's talk about that second derivative for a little bit more. The second derivative is a quantity of how much the likelihood function curves at the MLE, right? So we saw that the sigma squared over n was the sort of the well, it's not the second derivative is the curvature. It's related to the standard error. Standard error, that means talks about how curved it is. So when I said, hey, look, the curvature of this curve is really steep for the mean, but very flat for the variance, we could do the same process for the variance. We could derive the standard error or the variance of the variance. If that doesn't blow your mind, well, then you've probably been in the mixed model class. But in the sense of maximum likelihood, each one of our parameters will have a standard error to it. You don't often talk about a standard error of the variance in linear models with least squares because the variance is your mean squared error and it's sort of computed, but it's never ever do much with it. But it also has a variance to it. And I'll show you that right now, because of this, you can tell if you're thinking about this from the concept, if I just said that the standard error of the mean is it's related to the curvature of the likelihood function, you could also think that, well, the standard error of the mean um, told me, how much variability there would be in the parameter. That's right. So the standard error of the variance would talk about there'd be a whole lot more variance or whole lot more variability in what the parameter might be for the variance compared to the mean. And that's exactly right. It's a lot harder to estimate with precision the variance because the likelihood's a little bit flatter than it is to estimate the mean. But you can calculate it, right? How many of you have ever put a confidence interval on a variance before? But you could because you can calculate the standard error of the variance. All right. Any other questions about any of this before we get into the packages that implement this? All right. So the thing about maximum likelihood is, even though it's equivalent to least squares, your point estimates and your standard error should be equivalent. Um, Actually, implementing a maximum likelihood method for linear models is not the same, right? So uh, in LM, to do linear models in R, X is not part of the likelihood function. I showed you that before with Lavon. I had to somehow make it part of the likelihood function. Um, each of what I'm about to show you, X is still not part of the likelihood function, at least for NLME and LME4. Lavon will teach us that, and I think I'll have more slides on Lavon next week. Actually, I know I'll have more slides on Lavon next week. Next week is like Lavon week. Um, it's a path analysis software, piece of software, and structural equation modeling. But today, just to get the sense of what's happening in maximum likelihood and describe the effects, I'm going to use NLME and potentially LME4. These are mixed model packages in R. Um, they can be used for multi-level models, repeated measures analyses, and if you think really crazy about it, factor analysis methods as well too. Um, Basically, your LME and NLME are building a likelihood function out of normal distributions and multivariate normal distributions. So any model that sort of features those can be used here. Um, the mixed part, so NLME stands for nonlinear mixed effects, and LME4 stands for the fourth version of the linear mixed effects package. The mixed part refers to the type of model it can estimate. It actually estimates something called generalized linear mixed models. The mixed refers to parameters that are both random and fixed. So in that case, random and fixed parameters, the random effects are included in your model because you may not meet that assumption of independent and identically distributed. So the random effect sort of tricks a multivariate normal distribution into having non-zero correlation, and then the likelihood function is built off of those multivariate normal distributions rather than off of the univariate normal distribution. But the process still maintains the same. Right, so these mixed models extend our general linear model to be able to model dependency between observations, either within a person or a group or both. So if we were to build this for NLME, but both packages use a common but very general log likelihood based function based on the GLM, right? Basically, we are understanding that the conditional distribution of y given x is normal. We talked about that last week, right? So if we have y and we're predicting it with x and z, then the mean of the normal distribution will be given by our predicted value, right? Beta 0 plus beta 1x plus beta 2z plus maybe beta 3 times the interaction of x and z. And the variance of that distribution will be given by our variance of error or our residual variance. So therefore, we know from last week and how we derived it that y is normally distributed, conditional on its values of the predictors, right? So the likelihood function takes that log likelihood from the multivariate normal. Sigma squared now becomes sigma squared e. Y takes the place of x in our previous slide. And what we put in for the mean of y, I put as y hat, but that really is just this term up in the mean, our predicted value. Right? So now it turns out I have a likelihood function. I need to go and put it in, use either calculus or another system to find not one or two parameters before it was the mean and the variance. Now I have five parameters, right? I have the variance of error, that's one, and I have one, two, three, four regression coefficients. So you can think of that if I were doing a grid search, the grid would have five dimensions to it, which is not easy to go search over. So instead, I can tell you that there is a closed form, right? A set of equations for these beta weights and for any possible value of sigma squared. For any given value of sigma squared, there's a closed form for each of the betas, right? So if you pick sigma squared, these are the betas that will maximize your distribution, right? And so what NLME and what LME4 are actually doing are seeking to find values of sigma squared. So it's searching over sigma squared. For every value of sigma squared that goes in, they say, oh, I know what the MLE is for the rest. Use an equation. Calculate the log likelihood. Repeat, right, until you find a maximum. So this begins with something called a very naive guess. So basically, you can just start. You need a value of the variance to start with. You can use a value of 1, use a value of anything. And then it uses a process called Newton-Raphson to find a maximum. So Newton-Raphson is doing calculus, but with the computer. Sometimes we call this a numeric method instead of an analytic method, right? So what we do is we could calculate the log likelihood over a wide range of values of sigma squared, and for each person we could plot the likelihood values and see where the peak is, right? That take a while. So we each of us have things to do. I don't know about you, but we got snow to shovel this afternoon. I don't know how that's my fun. All right, go shovel that snow. Um, so instead of using a grid search, we could actually um, solve it mathematically instead by finding where the slope of the function is numerically, right? So step one, we could start with a guess of sigma squared, calculate the first derivative, we could call that d prime, of the log likelihood with respect to sigma squared at that point. And basically, with the value, we'd be able to tell, is our first derivative equal to 0, right? If we started over here, we know we're too high. And if we started over there, like if we started over here, if the slope was too high, positive, we'd be over here. If the slope was negative, we'd be over there. So we know where to back up or move forward, right? So you could think about this. We could say, oh, let's try a guess of sigma squared. Here's our first derivative. If it's negative, we've gone past the peak. If it's positive, we haven't made the peak. But there's information in the derivative to figure out where the peak is, right? So Newton-Raphson adds a second step, and it says it's going to calculate the second derivative, right? The slope of the slope to tell us how far off we are, and then to go figure out whether we need to adjust, right? So the second derivative, d prime prime, will always be negative as we approach the top, um, but we need d prime to be positive or negative, right? So basically, we could take a new guess, right? We could take our original guess of sigma squared error and make a new one by taking our old one and subtracting it from it the difference in the first derivative divided by the second derivative, right? And that is what we call Newton's method or Newton-Raphson. So to do this, we need to have an analytic function of the derivatives, but it works. The second derivative also tells you how sharp the peak is. We saw that before in other slides. So now let's do this in NLME real quick. So for now, we know that NLME will likely it's very much, we're just going to use it to look like LM, right? It's a kind of overkill. Like if we really just wanted a simple linear regression, we could just use LM. But I'm doing this to demonstrate maximum likelihood, right? If you took Lisa Hoffman's intermediate, you will have learned about the function GLHT. GLHT allows you to make linear combinations of your parameter estimates. By the way, those rely upon to figure out the new standard errors of the new linear combination that relies upon the asymptotic properties, the covariance matrix. But even GLHT works the same within LME, is basically what I'm saying. So we're going to start with the first model. It's empty, where IQ is the DV. An empty model means we're not predicting it with any predictor. And it turns out the empty model, the intercept for it is the mean, and the residual variance for it is the standard or is the sample variance. When you don't predict y with anything, but you put it in the linear model, it's y equals beta 0 plus error. Those terms give you the mean and the variance of y. And how you'd see that is basically what we saw the last time, right? If beta 0 was the only thing over here, and you weren't predicting it with x and z, it's just a symbolic substitution, right? If y followed a normal distribution and beta 0 was in the mean spot, beta 0 has to become its mean. So similarly, sigma squared has to become its variance. So here, The first model will be empty, where IQ is the dependent variable. And this links the GLS function from NLME to our previous set of slides. And after that, we're going to perform our previous analysis, predicting performance from IQ. And what we're estimating here is sigma squared E, the variance of IQ, and beta 0, which is our mean. So sigma squared E takes the place of sigma squared X, and beta 0 IQ takes the place of mu X. So the only difference between what we put in the statement for GLS and what we use in LM is method equals ML. So I'm forcing GLS to use maximum likelihood. Right? Okay, so I do that. I plug this in, and now we get different output, a little bit different output, right? At the very beginning, we have something called AIC and BIC and log lick. Log lick is our log likelihood. That sounds familiar. We use that. AIC and BIC are information criteria. They're functions of our log likelihood, the number of parameters in our model, and sometimes the sample size. BIC involves the sample size. And these are used to use relative comparisons across non-nested models. So we don't need those now. We're just looking at one model. And then the output from here, we see our coefficient. Our estimate of our intercept is 114.4, which is exactly what we found everywhere we went before as well, too. So nothing really changes with this, but I'm sort of starting to build the basis of taking the theory of maximal likelihood and putting it into our analyses. Do you have any questions at this point? Okay, in the absence of questions, let's take another 10 minutes, and I'll come back and share with you how we do the rest of this as well, too. All right, see you in 10 minutes. All right, so this is what we get from the output from the GLS function. I'm going to walk through a little bit of that as we go, and then I can show you as well in R if need be. In fact, I went and built this ahead of time. So the GLS function I'm just running is this one right here, and it looks very much like LM. You probably wouldn't know it's anything like LM unless you started looking at the output, and that's where, again, log likelihood shows up, and then you get other terms. So here, if you go and try to figure out what's in the object, there's a whole bunch of other stuff here. But the key thing in looking at is the number of observations and the number of parameters. So this is an interesting model because what it's optimizing is sigma squared. Even though we have two unknown parameters, for every given sigma squared, it uses a least squares function to figure out the mean. So it's really just searching over one thing. So this N describes the sample size, and P describes the dimensions that it's sampling over, in this case, just one. I will also note that REML shows up. REML is called residual maximum likelihood. The estimates from REML are awesome in that if you use REML, it is built to give you variance estimates that are unbiased. It's beautiful theory. But there are some features of REML that don't go well with what I'm about to show with ML, so I'm staying in ML. And REML really only exists right now in mixed model software for normal distributions. You don't see it in Lavaan and so forth, so it also fits through it. But I can I can tell you a little bit more about that in just a bit. So if we were to further unpack the output, you saw from the coefficients value right here, this is our value of our mean, our parameter, 114.4. Where's this residual variance? Well, it turns out they call it residual standard error, 205.9. If I take that and I square it, remember standard error is the square root of variance, we get our 4.24 that we've been estimating as our MLE for the variance. Okay, so these are our MLE values themselves. And we could, again, in theory, using MLE, we could figure out the standard error of the variance, like a standard deviation of a parameter. It happens. We don't see it here, but other programs actually provide that for you. Similarly, if I were to ask for an ANOVA table, we don't have a full ANOVA table here, in that we don't have like residual sum of squares, mean squares, all that other stuff. I'm going to talk about why that is in just a moment. But I did want to say one other thing. REML, if I were to go and estimate this with REML, then you would see our residual standard error, if I squared that, is the unbiased variance formula. So REML is what we default to. In fact, most of what we do in mixed models uses REML because we have finite samples and bias appears in finite samples, small samples a lot for variances. But this class is about ML, so I'm staying with that right now. Okay? All right. So there's our coefficients again. I mentioned that before. Here's our ANOVA table. The mean square error is no longer the estimate of sigma squared, right? This comes directly from the model estimation algorithm itself. So sigma squared is what's being looked for by LME in this function. So why that's important is, if you remember in linear models, if you had wanted to compare models where you keep adding predictors, right? Let's imagine you start with a model of y predicting x or x predicting y, and you want to compare that with a model of x and z predicting y. You can calculate the R squared for each of your models and use something called an R squared change test to come up with a p-value for it. Well, that's not exactly what's going to happen here because our ANOVA table isn't full. Right? That R squared came from our ANOVA table, and we could figure out p-values and stuff from that. We don't have that. So that's going to change a bit. But that actually changes to be some of the useful properties I mentioned at the beginning. Let's talk about those useful properties. I mentioned likelihood ratio tests or deviance tests, Wald tests, and information criteria as useful properties for why we use ML estimates. And so I want to show those to you. So let's consider our example where we wish to predict job performance from IQ, but let's just set our IQ at 114.4, right? Just to make the intercept more meaningful. You can tell I am influenced by Lisa Hoffman, who thinks every variable should always be centered. And I don't blame her. Centering's good, but that's where this comes from. We're going to estimate two models now, and both will demonstrate how ML can differ a little bit from least squares for these linear models, right? So we're going to start with the empty model where we just predict job performance by itself with just an intercept. And then we're going to add to the empty model the mean-centered IQ as a predictor. Okay? So the empty model, I can flip over here. Here's our empty model. Perf tilde 1 is just the intercept. There's our empty model statistics. We see that the average job performance is 12.8. We saw that in the beginning of class. Residual standard error is, if we square this, we could see the ML estimate, the biased version of variance at 4.16. We should have seen that. So we didn't see that at the beginning of the class, but that's our ML estimate. We know that it's smaller, it's shrunken. Right. So then I'm going to center our IQ variable. I'm going to call this IQ 114, just to note that it's centered at 1.14.4. And then I'm going to enter this into the model as a predictor. And again, both of these has method equals ML. If I'm using REML, I actually can't do this. So that's why I'm staying with ML on this. And here we can see this model. IQ has this regression slope of 0.96 and a p-value that's 0.0058. So it would indicate that we need to add it to the model. It improves prediction. But how do we test the hypothesis that IQ predicts performance? We can do that in two ways in MLE with maximum learning. Actually, we do it with three. I didn't mention one. It's a little more complicated. We can use something called likelihood ratio tests, or we could use Wald tests. The third way is called a score test. And each one of those involves fitting one or more of these models, right? We have two models at play here. We have a model without the predictor and a model with the predictor. Right? I just estimated both of those, and likelihood ratio tests are direct model comparisons. So you got to do the work of estimating the model that's smaller and the model that is bigger. And the other thing you have to have is the smaller model has to fit into the bigger model, be subsumed by it, be a subset of it, right? So what do I mean by that? Our empty model Okay. Um, can you hear me? Okay, great. Sorry. Somehow my AirPods switched away from my computer. I don't know what's going on. All right. So the microphone here, I'm sorry, microphone. The empty model is beta zero plus error. The model with the predictor has beta zero still in it. But now we've added beta one times this variable, right? So if beta one were to equal zero, we would be right back with our empty model. And that's what you need for the likelihood ratio test. You need to fit both the model that's smaller and the model that's bigger. And you have to be able to get to the smaller model from the bigger model through a parameter constraint, right? In this case, setting beta 1 to 0. They have to be nested models. Okay? So likelihood ratio test involves fitting both. Wald tests involves fitting the model that's more complicated. And it turns out score tests, which I'm not going to show you, involve fitting the model that's less complicated. All three of them in maximum likelihood converge as n goes to infinity. All three tests converge to the same result. So there's three different ways of sort of adding model comparisons. So if IQ does significantly predict performance, what percentage of variance in performance does it account for? We have to form an R squared, right? So it's relative change in sigma squared from the empty model to a conditional model. Let's start with the likelihood ratio test. The likelihood ratio test, which you may have heard of many times before, but this is where it comes from. So as your name implies, it's a ratio of likelihood values. So you can imagine if we have likelihood value for the empty model and likelihood model for value for our model with the predictor, the ratio of likelihoods is a division, right? Well, it turns out when we take the log likelihood now is a subtraction because the log of something that's a divided by b is really the log of a minus the log of b, right? So the likelihood ratio test is literally doesn't have a ratio when you're using log likelihoods. And using log likelihoods, it's literally this: the test statistic is the change in negative two times the difference in log likelihoods, right? So here, turns out the log likelihood for the empty model should be more negative than the log likelihood for the um, full model, H0 versus HA. But when you do that, and you use maximum likelihood, again, assuming asymptotic convergence, your n is big enough, this statistic I'm calling D follows a chi-square distribution with the number of degrees of freedom equal to the difference in the number of parameters between the models. So in our case, there's one parameter difference. Beta 0 is in our full model, whereas it's not in our empty model. So it'd be 1 degree of freedom, and we can compare this with a chi-square. Right? So what are we doing? We're forming a hypothesis test where the null hypothesis is beta 1 equals 0. Now, it turns out that null hypothesis is what you have to set beta 1 to get to the empty model from our conditional model, right? So if the null hypothesis was true, the empty model would be what we are using. But the alternative hypothesis is equal to not equal to, beta 1 is not equal to 0. So the difference between the empty model and the conditional model is one parameter, right? The empty model has beta 0 and sigma squared. The conditional model has beta 0, beta 1, and sigma squared, right? So there'd be 1 degree of freedom. We can estimate our null model log likelihood. That's negative 10.65. Our alternative model is negative 3.46. So negative 2 times the difference between the two is 14.4. If we use our chi-square function, we see that has a p-value with 1 degree of freedom. That has a p-value of 0.000148. So that we would likely reject the null hypothesis at most levels of significance, and therefore we would conclude that beta 1 is not equal to 0, or that it's needed to analyze our model. And it turns out if you take our two models and put them into the ANOVA function in R, that's exactly what's happening. The ANOVA function now knows there's a different, these are the log likelihoods. This is the test of models, 1 versus 2. There's your negative 2 times the difference in log likelihoods and the p-value that goes with it too. So when you add models to the ANOVA statement, it's now knowing, mainly because each of these model is a GLHT or a GLS object. It's a specific object, meaning ANOVA gets routed through a different function. It provides the likelihood ratio test for you. So likelihood ratio tests in maximum likelihood replace R squared change tests in least squares. Pretty cool, right? And why? Because that's what happens as n goes to infinity. Now, with 5 observations, n's probably not at infinity. So take this with a grain of salt, but that's just an example. Okay, Wald tests. So for each parameter in our model, you generically call each parameter theta. So this could be beta 1, for instance. Let's take our full model with beta 1. If we were to take the estimate minus what we want it to be, like to test its hypothesis for, so normally we set this equal to 0, and divide that by the standard error of the estimate, right, which comes from maximum likelihood. As n goes to infinity, this thing uses the property of asymptotic normality to say that that should be normally distributed with a standard normal distribution. So in a maximum likelihood sense, if we take our parameters divided by standard errors, we can always compare that number to a z-table to figure out its p-value. There is one exception is if you have bounded parameters. So if you're trying to test the variance is equal to 0, that violates some of the maximum likelihood regularity conditions. And so that it's not exactly right. Turns out your test is actually a little bit more conservative, right? Doesn't have a lot of type 1 error rates, but problems with power is more of an issue. We can further add that variances are estimated, switching the standard normal distribution to a t-distribution, right? So if you are estimating your variances, again, the same thing that happens with the finite sample, we want a correction for bias. The result, in fact, you can even see it here, this t-value is our estimate divided by our standard error. But because we have an estimated variance, we can actually show that the distribution of estimate divided by standard error follows a t-distribution, and in this case with 1 degree of freedom for the parameter. But that's not always the case. More often than not, z will be there, and z is sort of the limit of the t-distribution, right? So that's some statistics trivia for you. But Wald tests come with MLEs also, a built-in way to test our parameters. But remember, with Wald tests, we have to fit the full model, not the simpler model. Right? And so here's your example with the Wald test. How are we doing? All right, how do we do R squared? Well, in R squared, we actually have to calculate that ourselves. The empty model's R squared was, the empty model's variance was 0.416. The residual variance, once we estimated the full model, was 0.234. So to calculate R squared, we take the difference in each of those variances and divide it by the empty model's overall variance. You get a value that's 0.944, which is ridiculous, really high. How many of you have seen an R squared that high before in practice? It says 906 down there, so somewhere I got a mistake here, but let's just move on. All right. Another part we have is like information criteria. Information criteria can be used to compare models. Now, the likelihood ratio test, turns out this thing is something called a uniformly most powerful test, meaning if your models are nested, use it. But if your models aren't nested, you may have a problem, right? You can't use a likelihood ratio test. What's an example of a non-nested model? Well, if we want to compare, let's imagine y predicted by z with y predicted by x, they're not nested within each other. You can't set one of those parameters equal to 0 to do that. But what you can do is take a look at these information criteria. So if you look at a single column, the smallest value of the information criteria is the model that would be preferred, right? So AIC says model 3A should be preferred. BIC says model 3A should be preferred. Each type of information criteria gives a different value, meaning if you say, I'm going to use AIC, you may end up getting a different result than if somebody uses BIC. So information criteria are messy, but they come from likelihood theory. and they can be somewhat helpful, but only in the case when you have non-nested models. How we doing? All right. So, how does maximum likelihood and least squared estimation of GLMs differ? Um, as you may have recognized, the ML and least squares estimates of the fixed effects were identical, right? Where they differ is in the estimates of the residual variance. So if I used LM, my residual variance was thought to be 0.390. And if I used ML, my residual variance was thought to be 0.234. Right? The residual variance is too small in ML. So this could lead to problems when you have small sample sizes. So that's where we use REML, as I just showed you a few minutes ago. Right? How we doing? Okay, all of that's great, except what happens if I have missing data on my predictor? Anybody want to? It's list-wise deletion. You're right. So this is maximum likelihood, but we have to think about not just maximum likelihood giving us missing data protection. We have to have each of our variables in the likelihood function to make it work. So let me show an example for you here. I call this data. This is my live example. Those of you who've taught, you know how that feels, right? Uh, I'm going to start with a brand new data set. We'll call this data O2. And I'm going to take our first value of IQ and set it to missing. All right. How about that? So there we have it. Now, if I run the same model right here, now you'll note that that's not right. That's data O1. There we go. Now you'll note I only have 4 values. I have list-wise deletion again. That's not good. Similarly, let's try our 2 models. Let's go with model O4A, which is, oh wait, I just did LM, not GLS. Sorry, I'll show you this in just a moment. GLS, perf tilde 1, data equals data O2, and method equals ML. All right, so this is model O4A. Five total degrees of freedom. That's the number of people we have. There's 5 standardized residuals. You can see this is what we did before. But now let's try model 4A. Model 4A, we'll call this IQ114. And we'll call this model 4B with GLS. Uh-oh. Missing values in object. Doesn't even run. Not going to work. Not good, right? So what do we do in this situation? How do we get maximum likelihood where the predictor with missing data works? Anybody have any ideas? We can. In this one case, in cases that are small like this, we can. What we have to remember is that GLS is using a univariate normal distribution, but we can trick it to using a multivariate normal distribution if we try hard enough. Because the multivariate normal distribution is comprised of univariate normal variables. So how we can do that is a little bit harder, but let's see if we can do it. If we took data $sign $1 $sign IQ. So this is our IQ variable, right? and added to it, actually, I'll make this data O2. Our IQ, I'm sorry, this is IQ. Let's take performance and IQ, and we make it one long data vector right there. That's a place to start. I'm going to create a data frame here. Call this data O3. And in my data frame, I'll call this performance. Actually, I'll call this Y, a generic outcome Y equals. And here, I'm just going to give all of it. So this is a very lame data frame. It's not a whole lot to it. It's just a column of data. All right. So far, so good. Okay. All right. Now, this, by the way, this example only goes so far, but I'm showing it to say, what the heck, why the heck are we having to go to Lavon? Here's why, right? I can now create a series of dummy coded variables that indicate which um, value of y refers to which variable. Okay. So if I call this data O3 dollar sign perf, uh, perf indicator equals, and I'm going to do this, C of rep. Actually, hang on. Basically, I need to create a dummy coded variable that indicates for each value of y, if it's performance, it's a 1. If not, it's a 0. So here, 5 times, and then there we go. So now data O3 looks like this. The performance indicator is this one right here, right? Now, I'll do the same thing for IQ. I'll call this IQ indicator, and I'll do the opposite right there. So now data O3 looks like this. How are we doing so far? So now, if I go in and create a GLS, I could create, hey, look at that. GitHub Copilot knows where I'm going with this. If I turn off the intercept and predict Y with each performance indicator, it's like I have an empty model with one predicting the other. But I still have missing values. It's still going to do that. It doesn't allow any missing values. Okay. I guess I can't. But that's how we used to do things in back in the day. Um, used to, still do. Multivariate, multi-level models that Lisa talks about can be built this way. But what that would have done if this would have worked, and again, it's not working, is that, think about this, everywhere I had a performance indicator would be basically a value multiplying these. This becomes the mean of y, of performance. So that slope is the mean of performance. This slope is the mean of IQ. And now those variables are in the likelihood function. And it's up to me to figure out how to build it so that it has um, other data as well in it. In this case, we would need something to indicate that which person each of these values came from. But I don't have that. And I don't have the time for that here today. But why I'm saying that is, if you're using model packages like GLS, you might think you're using maximum likelihood, but you are. Oh, thank you for that. If I do na.omit, oh, nope, that didn't work. Oh, na action, sorry, na equals na.omit. Do I need to put quotes around this? There we go. Now it ran. There we go. And summary here is right there. Now I can get it to run, but um, it's not entirely correct because I only have one residual standard error, right? So that's a pooled standard error for both variables. Still not going to work too well. So did I see another question? JC, did I see you have raised your hand? Okay. So there are ways to sort of trick least squares packages into allowing us to have, or not least squares, but packages where there's only one outcome to having more than one outcome through a series of dummy coded variables and shutting off intercepts and so forth, right? But it's still not where we need it to get to. Um, Really, what I'd have to do to fix this a little bit more is I'd have to also include a basically a multi-level model that allows us to estimate a covariance matrix between the two variables per person, and that covariance matrix contains our regression coefficients in it. And so this is where, again, we always talk about maximum likelihood being important for giving us missing at random data protection or assumptions that we can believe in. But that's only if each of the variables apply to the likelihood function. And what we've built to this point, if I can get back to it, is a likelihood function that only involves y, not x. Right? So the only way we could make this work with missing data would be just like we'd use in LM. We'd have to do multiple imputation of some sort. And that process is a little bit lengthy and tiresome, but it's possible. Questions on any of this? There's my live example. Almost failed, but thank you, Vladimir, for saving me. Yeah. You mean here? I'm not. The model is specified with a single standard error. In fact, if I were to write the model out, it would look like this. Y equals beta perf. I guess this is beta zero perf uh, times perf IND plus beta zero IQ times IQ IND. But in this model, there's only a single error term. And so I knew the output would only be one error term, right? And it's pooled. But that's not what I need it to be, because that ignores the fact that the IQ variable may have a different standard deviation or variance than the performance variable. And so what I was trying to get at was this is one step that people sometimes use to start building missing data protections into likelihood functions when they have to use something like GLS or LME4's version of it. But it's problematic because it doesn't fully map onto the ideal model where both variables are part of the likelihood itself. And next week, we'll talk about what that ideal model should be. We'll build a multivariate likelihood. We won't be able to use this package to estimate, but we'll use maximum likelihood using a different package that moves forward. So the point I'm trying to build with this is, you might ask yourself, why are we picking Lavon? Can I just use ML and GLS? And the answer is absolutely not. Most likely not. Not absolutely. Most likely not, because GLS only has one outcome, one outcome allowed, and only estimates one residual variance. Did that answer your question? Other questions? Let me ask you a question. Why am I showing all this to you? I hope I made that clear. But let me ask, see if it's clear. That's a loaded thing I just said. I shouldn't have said that. I'd like to make sure that this is a check on my teaching. Let's put it that way. You're helping me understand if I gave you enough information to be able to say, why am I teaching you this? I believe that understanding how likelihood theory works is fundamental to understanding how to pick a likelihood system that builds your missing data into it. And I think that's part of what you have to look for. So I'm sort of going through some of the nuts and bolts of maximum likelihood, and I'll be doing the same in Bayesian as we go forward as well too, because I want you to understand a little bit about how features work, so that when you look at, some, if you're looking for every one of you will likely be using different packages and different methods entirely, right? Depending on your field, depending on the problem you're studying. Um, what I'm hoping to do, though, is give you enough of the skills and the knowledge of what likelihood theory does to say, wait a minute, I don't see a standard deviation for this other variable. Is it really in the likelihood function, or am I making more assumptions than I need to make? Because there is no one uniform way to solve missing data for most of what we're doing in this examples, these examples here. That's my hope. I hope that came through, though. And if not, I'm the person to blame. All right, other questions? Well, if there are no more questions, we can stop here. Let me just throw my wrap up slide, make sure I didn't forget anything here. It's our first pass at maximum likelihood. What I showed you today applies to all MLEs, not just the linear models. Um, it'll actually help us when basic assumptions are obviously violated. We can actually use maximum likelihood for a whole bunch of stuff. That likelihood function I built today could have different variants to it. Like, for instance, we could take our variance parameter and make multiple, like group based, or model it. Still fits in the likelihood function. Um, but maximum likelihood and maximum likelihood is a primary method for handling missing data that are assumed to be missing at random. But you got to use the full information, and that's why we're going to rely on the structural equation modeling methods or path analysis in our next class. Okay, at that, thank you for being here. Please stay safe and warm, the snow. And if any of you have any questions, I'm happy to stick around a little bit afterwards. So have a great rest of your afternoon, a great rest of your week, and I hope to see you next Wednesday. Hopefully the weather will cooperate and we'll be back in person. Take care.